Hi everyone, welcome back to our channel. Today we are going to discuss about the modeling of coupled circuits. So what is this modeling of coupled circuits is we have an coupled coil. So coupled means the meaning of coupled is the coils which are connected together is called as coupled circuits. So this is very important in our analysis part. So why? Because is so this modeling plays a major role in the designing as well as analysis of inductive circuits. Modeling means how you analyze and how you design the size of the inductor. This is called modeling. So you have to perform the modeling of the coupled circuits which are connected together. So now I am taking an AC source and I have some resistor due to inductance. I have an inductive coil and it is closed. I am taking this as a voltage of V1, a resistance of R1, an inductance of L1 with a dot at the starting. I have one more inductive coil where you can call it as a secondary. This is also an inductor. Inductor means definitely the equivalent circuit consists of an resistor. It consists of an resistor and this is excited with an one more source at secondary side. This is V2 and the resistance of this element is R2 and the inductance of this element is R2 and we have a dot which indicates, so actually a dot indicates the direction of induced EMF. What is the direction of induced EMF is given by dot, or it gives the direction. This direction we generally call it as the polarity of induced EMF is given by a dot. So that's why a dot is given here at the starting and here. So now we need to apply the modeling for this circuit. Very simple. So these are voltage source V1, V2 are voltage source. The resistor and inductor are voltage drops. So generally we'll write down applying an KVL. So apply Kirchhoff's voltage law at primary of the winding. Okay, so I am assuming the current of I1 is circulated. This flows like this, and here the mutual inductance is given as M. Directly M it is given. So now whenever the current flows here, the polarity of this is positive, negative. Whenever the current flows here, this is positive and negative. But here the source is like this. The current is given in this direction, which is I2. Entering is positive, leaving is negative. To this inductor, entering is positive, leaving is negative. So let's try to apply the Kirchhoff's voltage law at the primary. Okay, what is the voltage source? Voltage source is plus V1 and current is leaving. Actually I have to write down minus, but I'm writing directly as plus. So I have to write down this in left hand side, but this minus I'm writing in right hand side as plus, as voltage drop. The drop created here is I1 R1. So what is the voltage across an inductor? The formula for voltage across inductor is V equal to L di by dt in differential form. So therefore, the voltage across an inductor which flows here is nothing but the drop is L1 d I1 by dt, and there is a mutual inductance shown in the diagram. Here the current, so the current I is flowing entering the dot, but here the current I is leaving the dot in the coupled coil. When one is entering the dot, when one is leaving the dot, then we will be getting minus M into D. Mutual inductance is due to another coil, that's why it's minus M into di2 by dt. So this is how we can write down. But similarly, let's try to apply Kirchhoff's voltage law at secondary of the transformer. So the voltage is plus. What is the voltage? Plus V2 is the voltage source, and we have to write down this as drop. Actually I have to write down minus, but I am directly writing as voltage source is equal to, actually I have to write down voltage source minus voltage drop is equal to 0. Then we can write down voltage sources is equal to voltage drop. This I am using making use of. What is the input voltage given is V2, and voltage drop, what is the drop here? So I2 R2. So what is the voltage across an inductor? Voltage V equal to L di by dt. What is that inductance value? L2 d I2 divided by dt, and this is also associated with an mutual inductance. In this mutual inductance, to the coil 1 the current is there at entering of the dot, to the coil 2 current is there, I mean the current is flowing, the current is there at the leaving of the coil. Then I told, then we should get it as minus, so nothing plus into minus is minus, minus m, this mutual inductance is due to primary coil, which is nothing but minus m di by dt. This is how to write down the original KVL. But to overcome all this writing in differential form, let us try to analyze in AC form. Okay, so I'm giving an AC supply. I have an resistor, I have an inductor, and here also I have an inductor. Automatically this has some sort of resistance, this has some voltage source excited at secondary also with volt magnitude of V1 V2, and current flowing in the branch is I1, and the terminals and current enters this positive negative creates a drop of IR1, and here to this the current is entering at this point, to this the current flows as I2, and the resistance is R2, and the inductance is L2. Current is entering, this is positive, this is negative. So this is L1. This L1 I am going to write down in the form of an ohms, which is called plus J X L ohms. And here actually mutual inductance M is there. This also I am writing it as plus J XM ohms. Okay, so generally we call it as a resistor in DC as ohms, and inductor as Henry, and capacitor as Farad in the case of an DC supply. In the case of an AC supply, we call directly as ohms. This inductor we can write on it as plus J XL ohms, which is also equal to plus J XL is equal to omega L ohms. In the case of a capacitor, we'll get minus J XC ohms. This we can write down it as minus J divided by, this can be written as omega C ohms. The ultimate units are here. So this is like with respect to self inductance, we can write down with respect to mutual inductance as plus J omega L. Omega L you can write down, this L you can write down it as XM ohms. Now that's how we have written this XM ohms. Now let's try to link with respect to this. Now this is also like acts like a resistor with the terminals positive and negative. Whenever the current is flowing, this is positive terminal, leaving is negative terminal. Whenever the current flows, this is positive terminal and negative terminal. So let us try to apply Kirchhoff's voltage law at primary or at input. Whenever you see here, so actually the polarities I am sure AC should not mark polarities, but why I am marking this to make the things very clear. It is an how we are applying the KVL. Okay, so apply the KVL. Voltage source is plus V1. Voltage drop is, the drop is I1 into R1. So I1 R1. What is the drop whenever it is an resistor is? So this is plus I1 into plus J X L1 ohms, and this has an mutual inductance of plus J. So this plus into, so what is the value when current is entering the dot and current is leaving the dot? Here the current is leaving the dot and entering the dot. I already told we will be getting minus J X M ohms. Okay, this is with respect to primary. Similarly, let us try to apply Kirchhoff's voltage law at the secondary of the transformer or secondary of this coil. So the input voltage we are applying is V2, so therefore voltage source is V2, drop is I2 into R2, and the drop, this inductor is stated as, what is this inductor value? This is plus J X L 2 ohms. We can write down this as plus I2 into XL ohm is nothing but plus J XL 2 ohms. And here you can see, here current is entering the dot and current is leaving the dot, automatically you will get minus, which is minus I2 into mutual inductance is J XM ohms. So now let's try to expand it and write down in a systematic format. So this we can write down, V1 is equal to I1 R1 plus I1. So XL can be written as omega L1 minus, plus into minus is minus. Xm can be written as minus, is nothing but omega m multiplied with the value of I1. Here you can write down this, you can write down V2 is equal to I2 R2. This is nothing but I2. XL2 can be written as omega L2. XL can be written as omega L2 minus, here the current, this inductance is not due to the first coil, this inductance is due to the second coil. So why? Because this mutual is due to the second coil, this mutual is due to the first coil. This is small modification. So here you are going to get 2, and this is minus I1 into XM can be written as omega m ohms. So now by segregating it, the terms of I1, so when you separate the terms of I1, V1 is equal to I1 into R plus omega, XL can be written as omega L 1 ohms minus J omega M I2. This can be separated as taking I2 as a common term, I2 into R2 plus J omega L2 ohms minus I1 into omega is nothing but minus j xm ohms. So when you write down in a standard format, you can write down in a matrix form. So this is nothing but V1 I1 Z11 plus I2 Z12. V2 is equal to Z21 I1 plus Z22 I2. So when you write down in a standard matrix format to understand the things, so this is the value of Z12 and this is the value of Z22 and this is the value of Z21. So you can write down from the above, Z11 is equal to R1 plus R1 plus J omega L1. So this is nothing but J will get repeated. X can be written as omega L, so J gets repeated. Okay. So and Z12 is equal to only I2 is separate, we'll get it as minus J omega M. So similarly Z21 we can write down it as minus J omega M, and Z22 you can write down this as, so here J gets repeated and J gets repeated, is nothing but R2 plus J omega L2. So this is how we are going to get the values of R1, sorry, Z11, Z12, Z21 as well as Z22. Here you can see here the this Z12 and Z21 are of same value, Z11 and Z2 are different. So this is called symmetry and these conditions are called reciprocity conditions. This is how we understand. In the upcoming class, we'll try to understand about the modeling of a transformer as well as in parallel circuit. If you feel the content is useful, please like the video, share with your friends. If you have any doubts, let me know in comment section. And if you're watching the channel for the first time, subscribe the channel. This is a free channel for the betterment of students and faculty. Yours obediently, Ram. Will meet in the next video.